Stanford University.
Thank you very much. It's a pleasure and privilege being here. Well, I think the title says everything. So let's get started right away. If we look at the developments of the last century, I think innovation and growth are two of the attributes we can use. And in terms of growth, I'm depicting here two developments. On the upper left, that's the world light-duty vehicle fleet. So these are the automobiles and light trucks, which have grown essentially from zero at the beginning of last century to about 700 million at the beginning of this century. And most of these vehicles still operate in the industrialized world, which account for about 15 to 20% of the world population only. So enormous growth we can expect to come from this upper segment here, which corresponds to all other countries. A similar development in terms of aircraft revenue passenger kilometers is shown here on the right. The growth has been a little bit delayed to after World War II with the introduction of the jet engine, which provided the productivity that was necessary in order to generate this upward development. Now, these developments have generated many benefits in terms of living standard and quality of life, but at the same time, they have produced things we don't want, traffic congestion on the road or in the air, as we can see here for the US on the lower left. And they also consume lots of energy, and transportation, in particular oil products. Transportation systems nearly exclusively operate with oil products. And what we see here is the growth in oil products from 1900 to the beginning of this century in the United States. And we see that most of this growth has come from transportation. Now, oil has a number of, or the demand for oil has a number of implications in terms of energy security with regard to oil imports. But also burning oil generates greenhouse gas emissions. 1 kilogram of oil, roughly 3.2 kilograms of CO2. That's simple arithmetic. And if we release that CO2, I think I don't have to comment on this chart here. We can download the data from the internet. It shows the atmospheric CO2 concentration, which has increased from a pre-industrial 280 ppm to almost 390 ppm today. And if we want to stabilize the development, let's say to about 2 times the pre-industrial level, which would be about the ceiling of this room, then we would need to implement draconian changes. This is a chart from the Stern Review, which was published in 2006. The blue line is the sort of baseline emission trajectory, and the other lines that go that bend downwards correspond to different stabilization levels of CO2 equivalent emissions in the atmosphere. A 2 times pre-industrial stabilization level would require that we achieve the maximum of CO2 or greenhouse gas emissions in this case within the next 10 years and then start mitigating. And obviously, if we wanted to stabilize the CO2 equivalent concentration at lower levels still, then we would need to start mitigating essentially today. Now, whether we will achieve that or any of these trajectories will increasingly depend on the transportation sector. Namely, with economic growth, transportation continues to grow in terms of absolute and relative importance. As economies develop, the composition of GDP changes too. Initially, most of the GDP is generated in the agricultural sector, then with the beginning of industrialization, the industry sector, and later on in the service sector. Now, each of these 3 sectors consumes energy, so we can expect a very similar development in the energy system. And this is what is shown here. So let me guide you very briefly through this. On the upper left, we see the residential sector, the share of final energy, plotted over GDP per capita. And if you imagine villages in Africa or India or China, the main energy demand they have is heating and cooking. So, as a result, nearly all of the energy is consumed in the residential sector. Now, with the onset of industrialization, more energy is used in industry, and the share in residential sector declines because of the stronger increase in the industry sector. Once the economy is industrialized to a certain extent, and the society moves towards a post-industrial society, energy use in the service sector grows more strongly. And within the service sector, transportation is the most energy-consuming component. So what we see is over the long term, a systematic shift towards transportation energy use and CO2 emissions, which is simply an impact or the result of economic development. In the US, transportation accounts already for about 40% of final energy use. Highest income country, still significantly smaller in less developed countries, but the trajectory is very much the same. In terms of CO2 emission, the US energy economy contains about 33% of CO2 from transportation. On a global scale, it's about 1/4. The data here range from 1971 to 1998, and the corresponding color coding here for the 11 world region here is given on the right. Typically, the first data point is 1971, and the last one is 1998. So what are the key questions that we want to look at today? Well, if you want to mitigate greenhouse gas emissions, what are the key technological opportunities? That's what I'm going to spend some time on. And if it was so easy and there weren't any constraint, we wouldn't have to look at the second one. What are the main constraints in doing that? And as I'm going to show, is there are promising technology opportunities, but these low greenhouse gas emission technologies are more expensive. And consumers, or most of the consumers, under current energy prices, would not voluntarily adopt them. So we need policy measures in order to introduce them. And what we also would like to look at then is what is the impact of these policy measures on transportation demand and on the technologies that are going to be adopted. So much of what I'm going to say is actually summarized in a book that I wrote with 3 colleagues from MIT, and their names are given here on the upper right. So I have to pay tribute to their co-work here in this area. And much of the data I'm going to present can be downloaded from this website. So feel free to do that and play around and do your own analysis. What we did is we took, as we would think, a comprehensive approach. We look at both demand side and supply side. Many studies exist that look exclusively at the supply side. This makes, of course, sense in order to understand what is the potential for various technologies to mitigate greenhouse gas emissions per unit activity. But given the long timescales that may exist in order to put these technology opportunities into place, the absolute level and the composition of demand may have changed. So we may want to look at both of them. And as I'm going to show, it's really important to look at the demand as well. Well, we are looking at a global issue, and that's why we are looking here at a global scale. A personal bias of myself is that we can only limit the range of plausible futures if we understand the past. So there's quite some look at historical data. And what we need is an analytical framework to put all the components together. And this framework can be very simple. And this is what we use. So greenhouse gas emissions, that's the GGE, equals greenhouse gas emissions. And then we can expand the right-hand side by energy over energy and passenger kilometers traveled over passenger kilometers traveled. 1 passenger kilometer simply being 1 person traveling 1 kilometer or 2 people traveling half a kilometer each. So if we do that, then we can structure our approach and problem. So all other factors equal, any increase in passenger kilometers travel will result in a proportional increase in greenhouse gas emissions. So that's a purely behavioral component here. Then the next factor, energy over PKT, that's energy intensity, how many megajoules we need to travel 1 passenger kilometer or passenger mile, is both a technological and a behavioral component. It is technological because of the performance of the transportation system that you look at, but it's also behavioral because you purchase the transportation system or the service of a transportation system, and you can use different modes of transportation. And there's also embedded here the occupancy rates, how many people are actually sharing a particular transportation mode. And the last component, greenhouse gas emissions over energy, is a purely fuel-specific characteristic. How many grams of CO2 are being released if you burn 1 megajoule or 1 unit of any given fuel. And in order to look at that systematically, we need to conduct a life cycle analysis. So the game plan now is we will start looking at passenger kilometers traveled. Then we look at the evolution of energy intensity. And then we look at each of these components and try to understand, well, at these two, and try to understand what opportunities do exist, what technology opportunities do exist to mitigate greenhouse gas emissions. Then we look at the policies that exist, or the policy options that exist to implement these changes. And at the end, as time remains, hopefully, we will try to put everything together. So we'll start with passenger kilometers travel demand. What I'm going to show you is that there are surprisingly simple, fundamental characteristics of human travel behavior. The amount of money and time spent on transportation, on average, first discovered by an Israeli transportation researcher Jacob Zahavi in the late 1970s and 1980s. He has built urban transportation models. We have applied those in a sort of bigger context. What I'm going to show you is the simplest plausible model that you can think about that tries to understand the historical evolution of passenger transportation on a global scale and projects plausible future levels. I did this jointly with David Victor, who some of you may remember has been a faculty member until recently here. And what I'm currently doing during my sabbatical is to make to formulate a more sophisticated model that takes into account prices and a utility function of functions of the various modes involved. So let's start with these two characteristics of travel behavior. Now, most predominantly, and perhaps to some extent surprisingly, people spend a roughly constant fraction for their travel on average. We see here numerous different settings from around the world, and they suggest that irrespective of the income level, which ranges from essentially $0 to $35,000 per person per year, people spend about 1 to 1.5 hours, or roughly 5% of their time traveling per day. This applies to African villages, these are these red data points, to Palestine, where people are very much constrained and moving around, to Eastern European cities, Asian cities, and Western European countries, and the US, of course. So this is one very fundamental characteristics we need to remember. I would love to go more into detail here, but in the interest of time, I think I have to move on. The second one is the fraction of income spent on transportation, which is also remarkably stable, at least from the time on when people on average, or households on average, own at least one automobile, namely about 10 to 15% of income, or as shown here, is a share of GDP. It's roughly 5 to 10% of GDP. So if the fraction of GDP spent on transportation remains roughly constant, and GDP continues to increase, then total travel demand increases at the rate of GDP, more or less at least. And this is shown here. So we have passenger kilometers traveled per person over GDP per person on a double logarithmic scale for the same 11 world regions we had at the beginning. And as we observe, they are all moving towards one direction, namely higher levels of passenger kilometers traveled, the richer they are. This is true for North America. That's the black trajectory here, 1950, the first data point, and typically 2005, the last data point. Or for centrally planned Asia and China, which has caught up tremendously over these 56 years, and all the other regions in between. Now, there are, of course, differences at a given level of GDP per capita, which can be explained by different prices for real estate and transportation. But that's not of interest here at the moment. So if these regions develop in accordance to GDP, then again, with rising GDP, also in future, we would expect an increase in travel demand. Now, the theoretically highest level of mobility would be achieved if all inhabitants of all regions traveled with the fastest mode of transportation over the entire travel time budget. So this, and we assumed here 600 kilometers for aircraft, gate-to-gate speed. 600 kilometers times 1.2 times 365 is about 280,000 kilometers per year. That's what you can, in theory, achieve. And at that level, at that high level of demand, much of the travel would be international or interregional. This means prices to adjust, income adjusts, and all of these world regions theoretically would meet in one distant hypothetical point at the end of this shaded envelope, which is shown here. So this admittedly very simple model suggests or would imply that you formulate one and the same regression equation through each of these historical trajectories. You constrain one of the parameters or coefficients such that the equation has to go through this point. And then depending on your projection of GDP per capita and population, you would have a projection of total passenger kilometers traveled. So we said that with rising travel demand and a constant time budget, we have to get faster. Now, this is what is shown here in terms of low-speed public transportation modes. That's the share of these modes over passenger kilometers traveled per person. Again, for the same 11 world regions, and we see that all of these regions develop along the same trajectory or within the same envelope, but one of them, that's the blue line that is sort of upward bent, which is sub-Saharan Africa, which is an aggregation issue. If you again look at the black curve, that's North America, we see that it's exactly in the same envelope as the other subsequent regions. So typically the US is suggested to be extremely dependent on automobiles, and public transportation doesn't play any significant role, but we see that this can be explained to a large extent because of the high level of income and associated level of passenger kilometers traveled per person. The other world regions are on the same trajectory. Now, the decline occurs because people shift to the next faster mode of transportation. What we see here is the share of light-duty vehicles, again in percent of total passenger kilometers traveled, over the same x-axis. And we see the many 85% of the world population that is currently motorizing, while in the higher income regions, North America, the black one, and Western Europe, the yellow one, the relative importance of automobile travel has already declined. And this, again, can be explained from the perspective of this simple model, that these modes are not fast enough to stay on the growth trajectory of total travel demand. We see here, especially these two regions have already heavily gone into high-speed transportation, which is, in general, air transportation, high-speed rail. And the consistency of this model using the target point would then suggest that at the ultimate level of demand, 280,000 kilometers per person, the share of low-speed public transportation and light-duty vehicles would be 0, while everybody would travel by high-speed transportation. Now, obviously, were we going to end up here, at what level this needs to be examined still, it is, from today's perspective at least, unlikely that we will ever move at that hypothetical endpoint. So, if we combine the absolute levels of travel demand and the mode shares that we have just projected, at least the basis of it looked at, then we have the results here. The industrialized regions here on the left, passenger kilometers traveled in trillion passenger kilometers, very small in the 1950s, nearly 20 trillion in 2005. And then what we used are two different rates of economic growth from two different studies, which then suggest roughly a doubling by 2050. It's different in the other regions, which are dominated by developing countries. We already experienced a significant growth between 1950 and 2005 to about the same level as the industrialized countries. But then we have a 3- to 6-fold level projected by 2050, mainly because of higher income growth and higher population growth. The shares of the various transportation modes are also illustrated in this chart, with yellow being high-speed transportation, red low-speed public, and blue light-duty vehicles. And we see that light-duty vehicles would remain at about the same level or even slightly decline in the industrialized world, and nearly all the growth would come from high-speed transportation modes, whereas in the developing or mainly developing regions, most of the growth will come from automobiles because they're sort of lag behind in the development. But later on, especially as we grow faster because of high economic growth, a significant fraction will then also come from high-speed transportation. Now, this is, of course, a very simplistic model, and as I already mentioned that I'm working on a more sophisticated version that takes into account more constraints. But what we can do is look at some of the omissions that we did by modeling this and then question, well, would any of these potential constraints have a significant impact on the projected level of mobility or choice of modes? And here are a few examples. In order to remain on the growth trajectories, we need to, growth trajectory, singular, we need to continuously increase mean travel speed. And there are two potential constraints I can think about that may actually prevent us from doing that. One is that we continuously need access to availability of high-speed transportation modes. Well, there have already been attempts in terms of air taxi services and supersonic transport. They have economically not succeeded, but there's no reason why this shouldn't be tried again. Traffic congestion may perhaps be a more severe constraint. But also here, if we look at this issue, you begin to realize that there are opportunities, and there have been opportunities over the last several thousand years. Traffic congestion was already a big issue in antique Rome, and Julius Caesar, I believe, was the first transportation policymaker who has introduced laws that would ban wheeled vehicles from entering Rome during the daylight. By the way, a policy that still exists in a number of Italian cities, city centers. But what people have been doing, they have learned to adapt to traffic congestion by traveling at different times of the day, traveling different routes, or using different modes. Governments have supplied more infrastructure. Industry has provided traffic navigation systems. People have equipped the vehicle more comfortably with radio and stereos. And what also happened is, I missed the last point now. Never mind. So this is one adjustment mechanism. And then also what we saw in the previous chart is that that automobile travel industrialized world is already saturating and potentially may decline over the long term. So we may have actually reached the peak of automobile travel. It's a different issue in air transportation where traffic is growing at very high rates, as we have seen, but also there exist technology opportunities to further expand the infrastructure. Very quickly, telecommunication, is it a substitute or a complement? That's the main question. If we look back over the history of telecommunication transportation, it doesn't occur that there has been any net substitution. Some of the innovations may have replaced traffic as a first-order effect, but these telecommunication systems have then generated more linkages and opportunities to travel so that overall it occurs that there has been no net replacement. If you think back about the paperless office that people have projected in the 1970s, well, guess what? We are using more paper than at the 1970s per person, but the way we use paper has changed. Probably similar here. Energy resources. Do we have enough energy resources in order to satisfy our projected levels of traffic demand over the next 40, 50 years? Well, there's lots of stuff in the ground. Perhaps not high quality light oil, but many other resources. And recently we heard a talk about oil sands and the associated enormous resource base that comes with it. So unlikely that this would become a binding constraint over the next 40 years. One issue, of course, is the geographic location. But given the large number of alternatives, this probably doesn't become binding. Environment, this is something I would like to address further. And this was one of the questions we wanted to pursue, will global warming policies impact the growth in transportation demand that we have seen before? Okay, let's move to the second factor. how much energy we need per passenger kilometers traveled. And if we look back over the last 50 to 100 years in terms of transportation system development and the technological progress that has been achieved, we could actually imagine that there has been an enormous reduction in energy per passenger kilometers traveled. So total energy used in passenger transport divided by total passenger kilometers traveled. Well, unfortunately, the trends have been in the other direction for most countries. The US is indicated here in purple from 1950 to 2005 in megajoules per passenger kilometers. Japan has more than doubled its energy intensity, as has Germany until the reunification. France and others have remained roughly constant. Now, there are the good reasons for that increase. What has happened essentially over the last couple of decades is that the occupancy rate, so the number of people sharing a vehicle, has drastically declined as a result mainly of the increasing female participation in the labor force. Women have become more active in the labor market. As a result, household size has declined and the vehicle fleet has gone up, which reduced the need and opportunity for sharing a vehicle. In the US alone, this has been responsible for about 30% increase in energy intensity, and we observe very similar trends in other parts of the world. And here are a number of other reasons why energy intensity has gone up and may continue to do so. I can't go in detail in everyone, but one obvious one is a shift towards more powerful vehicles. As we get richer, our expectations in terms of quality and comfort and safety also increase. And there are more, and unfortunately, I think because of time constraints, I have to move on, but I'm happy to discuss them later on. So perhaps one brief excursion here to the shift towards larger, more powerful vehicle. Well, there has been consumer demand. Consumer demand exists always for safety, comfort, and so forth. But consumers always had to balance these attributes with the income that they earned. Now, household income has grown significantly faster than the price of the average vehicle. And as a result, people have got better access to these larger and more comfortable cars. Another enabler has been the manufacturer competition for market shares. Because of the overcapacity in the vehicle market, competitors, they compete on financing schemes. They provide larger models for very little extra costs. And also they offer leasing contracts that allow you also to move around in a bigger and more comfortable car. And ultimately, of course, low fuel prices. So one example, some of us may remember the 1983 Toyota Camry. The 2000 Camry, that's a real automobile, at least from today's perspective. But this has come with a number of attributes that lead to this increase in energy intensity. So the curb weight has gone up by about 35%, engine size by 20%, engine power even by 70%. So that's quite an engineering achievement here. But at the same time, fuel consumption has increased by 20%. So even if you stay within the same model, you are going to, at least in the past, you have increased energy use. So if we combine the projection of passenger kilometers traveled and energy intensity due to a number of factors, of which I could only mainly discuss shift towards larger vehicles, then we've got an even larger increase in total energy use as suggested by passenger kilometers traveled alone. If you only look at the yellow line here, so the relative level of energy use in 2005 was 100. It was more than 10 times the level from 1950, and it could triple to quintuple, or roughly triple to quintuple by 2050, if we assume a constant technology scenario, which means that the best available technology is going to be introduced over time and there's no further technological progress, which should be the case in absence of any climate policy and at very low oil prices. So what can we do about it? Well, energy over PKT we can decompose in energy over vehicle kilometers traveled times the inverse occupancy rate. And what I wanted to do now is look at this energy over VKT for a few minutes. And this is simple engineering. That's the combination of the first law of thermodynamics and the equation of motion. And what it suggests for road vehicles that energy used per distance traveled is or equals 1 over the propulsion system efficiency, which is engine and transmission, times the sum of the driving resistances. That's acceleration resistance, that's the inertia of the vehicle essentially. That's rolling resistance, very strongly dependent on the mass, such as the acceleration resistance, and of course on the surface of the road and the tire characteristics, and aerodynamic drag. So if we were able to reduce the driving resistances by 20% or 25%, and you increase the propulsion system efficiency by 25%, then you have 3/4 over 5/4, so you have 3 over 5, 6 over 10, 40% reduction in energy use on average. So if you can achieve that, that's quite an achievement actually. Similarly, for jet aircraft, you can derive a similar equation. That's the so-called Breguet range equation, now a little bit modified so that you have on the left-hand side, you've got the energy intensity. But that's the same approach. It's a bit more difficult because airplanes tend to lose mass because of the enormous amount of fuel they carry and burn. So you have to integrate over the weight of the aircraft, and this gives you this logarithm here. But what it says essentially is that the less fuel the engine burns, the lower specific fuel consumption, the higher the lift-to-drag ratio, that's the aerodynamic efficiency. And that's a bit difficult to see from this expression, but the lower the ratio of structural mass to total mass, the less energy you will consume. Now, it doesn't mean that if you fly faster, that you reduce energy intensity, because these expressions are, of course, correlated, and your lift-to-drag ratio would go up, for example, such as engine fuel burn. Now, looking at these equations alone, and we see that it's very similar in terms of the determinants, we could imagine actually it's straightforward to reduce fuel burn. Let's take some mass out, let's take some of the drag out in both equations, and let's increase engine efficiency, and we've got a much more fuel-efficient transportation system. Now, the bad news is that there are many constraints associated with that. There are trade-offs. I don't need to go into detail. Yeah, you can read it yourself. There are enormous consumer acceptance issues. Just think about the range anxiety of electric vehicles or comfort issues with aircraft. And there's enormous risk with regard to the development of new transportation systems. The vehicle industry is very capital intensive, and as a result, designers and companies are very careful about developing new vehicles, and they use often proven designs based on which they develop new models. And as a result of that, many of the technologies we're discussing today have a very long history. Now, on the upper left, that's a hybrid electric vehicle. I believe the first one developed by Ferdinand Porsche in around 1900. And it took 95 years until the first commercial application has been put in place. Now, on the lower left, this is one of the many designs that existed at the beginning of last century for a blended wing-body aircraft. So, as you see, it mainly consists of a flying wing, because the intention is to get rid of all those surfaces or components that don't generate lift. And the crew and the passengers would then be located in the wing. Now, it's typically military applications are in aviation the first step towards commercialization. And the B-2 bomber was the first one here, and it took some 70 years to put that into place. And whether we will ever see a commercial application such as this one, it would definitely take more than 100 years. So having these timescales in mind, we, and this is mainly John Haywood and Ian Waits and myself, we looked at the various opportunities and built simple models in order to assess what can we expect based on the technologies that are currently under development if we implement those in automobiles and aircraft. And our conclusion was that we could reduce energy intensity by about 30 to 50% over the next 10, 15, perhaps 20 years. And then it would take another 20 years or so until these technologies get implemented to a significantly large extent in the transportation sector in order to experience a benefit on the level of the entire vehicle fleet. Now, unfortunately, as I mentioned at the beginning, reducing energy use while maintaining all other vehicle characteristics, that's important, is expensive or can become expensive. This chart shows a typical cost curve for reducing automobile fuel consumption. Now, starting from a reference vehicle, here in the bottom with about 9.8 perhaps liters per 100 kilometers, we can reduce fuel consumption by implementing additional fuel-saving technologies or making some technology changes. As can be seen here, the first 20–30% can be managed at relatively low additional costs. You tweak a little bit here and there in terms of engine and vehicle structure and aerodynamic drag, and these are relatively low-cost measures. But at one point, you need to implement more substantial fuel-saving technologies, and the costs go up. So, for example, you may need to introduce material changes. You need an aluminum-intensive or carbon fiber body instead of a high-strength steel body, or ultimately, you may need to implement a hybrid electric drivetrain that would bring you then to the low reductions in energy use that you may want to aim at. So, very briefly, the last component here, greenhouse gas emissions over energy, which is a fuel characteristic, as we pointed out. Now, there are many requirements for transportation fuels, and environmental impact is only one of them. I don't need to go into detail, but obviously one of the most important ones is high weight volume characteristics, high energy content per unit weight and volume, because you don't want to carry around lots of mass and volume of transportation fuels. And what you need to do, of course, in order to understand the implications of using alternative transportation fuels is to look at a life cycle basis in which you take into account the amount of energy consumed and CO2 emission released for the production and supply of any of these fuels you're looking at. So in the top row, we see energy intensity in terms of megajoule per passenger kilometers. In the bottom row, we see greenhouse gas emissions in terms of grams of CO2 per passenger kilometers. And the left panel only shows petroleum-based fuels, whereas the right panel opens up the range of alternatives to include also alternative fuels. Now, what we can see from looking only on the left panel is that there's an enormous potential for reducing fuel consumption from about some 2 megajoules per passenger kilometers to below 1. And each of these steps we see here is one discrete technological change, and we end up with a diesel-fueled hybrid electric drivetrain. Then we look at alternative fuels, and just to pick out a few of them, most promising is ethanol from cellulosic biomass, second-generation fuel, which would significantly reduce life cycle CO2 emissions based on the respective, compared to the respective reference vehicle. You see there's no yellow bar here, and for that fuel, so on-the-road emissions are 0 because of the assumption that this is renewably produced biomass, and the next generation would then absorb the CO2 released from that particular vehicle during the growth phase of the biomass. CNG can generate some benefit. Oil sands would slightly increase life cycle energy use. We heard this presentation a few weeks ago, not mainly, but only because of the larger amount of processing energy for gasoline from oil sands, which compares to this one here, about twice as large. And what we also see is that coal-based fuels, if we sequester the CO2 emissions at the fuel plant, can have a significant benefit in terms of CO2 emissions. These are fuel cell vehicles, the last 3 here on this side. And if you produce hydrogen from coal and sequester the CO2, then we see that we can achieve very low levels of CO2 emissions. So we shouldn't discount any of the fuels that we have on the table, neither if it's coal. Now, there is a significant scale challenge if we go to alternative fuels. Now, this is the approximate number of nuclear reactors that exist in the United States. All of them has 1 gigawatt. And now the question is, how many additional nuclear reactors do we need if we wanted to shift very quickly to a hydrogen economy, at least for light-duty vehicles, that uses hydrogen only from zero or close to zero electricity. And the only way of doing it today on a large commercial scale would be nuclear electricity, which powers then electrolysis plants. And you see, I've left here a little bit of space here below these. And the scale of the US transportation system alone would suggest that we would need about 900 nuclear reactors in order just to substitute the existing use of gasoline. Now, obviously, fuel cell vehicles are more energy efficient, so you don't need 900. You can do it with 2/3. But 600 is also quite a large number. And this generates the beauty of petroleum fuels that come out of the earth in very high energy densities and make our life so pleasant if we discount climate change and energy security. So, policy. How can we introduce the low greenhouse gas emission technologies that we have been looked at? Well, the objective is to rebalance consumer preferences. Consumers like cup holders in the cars, they like horsepower, they like comfort, safety, and they like fuel efficiency. They like all of them. But what policy measures then try to attempt is to rebalance these preferences and assign a higher relevance to fuel economy as compared to other attributes. And when you achieve that, then you would also induce industry to put more resources into producing these vehicles at a faster rate and at a larger scale. And the options, I don't need to go into detail, market-based measures which put a price on the externalities, but give the consumers a choice. Regulatory measures which, for example, performance standard, which constrain the technological characteristics of vehicles, for example, and research and development. There are a number of criteria one needs to take into account when formulating these policies, and some of them are indicated here. Economic efficiency, well, they favor generally market-based measures. Time to impact, similarly, because market-based measures also typically affect those technologies already in place. Don't have to wait until the fleet is turned over. Consumer acceptance, well, regulatory measures tend to hide the extra costs from consumers, and as such are or have been more widely accepted, and as a result, many environmental policy measures, or partly because of consumer acceptance, have been implemented as regulatory measures. An important one is also interaction with measures already in place. Already we have a number of measures. We have fuel economy standards, we have low carbon fuel standards, we have subsidies for biofuels, for electric vehicles, and so forth, R&D and whatever. And if we impose another measure on top of these, we may actually increase economic distortions. Transparency is an issue. What happens with the revenues of a CO2 tax? Equity, do those that earn less and are socially disadvantaged, would they be hit harder than other layers of the society? And the impact of the measures we can see very plausibly here on this very simple identity again. So if we impose a carbon tax, for example, on our transportation or our energy system, ideally, we would affect all three of these components favorably. We would make the costs of less carbon-containing fuels more attractive. So we would make carbon-containing fuels more expensive. We would increase the cost of driving, so people would choose more fuel-efficient vehicles. And there's also a small fuel price elasticity, or travel elasticity, and people would slightly reduce the travel. So all of these factors would go in the direction we actually want. Now imagine you imposed a tightening of the fuel economy standard, which has been done. Then this would leave the greenhouse gas emissions of energy largely unaffected. It would reduce energy over PKT, that's energy intensity, but it would slightly increase passenger kilometers traveled because of the rebound effect. The marginal cost of driving would decline. As a result of that, this would increase. So we need a very tight fuel economy standard in comparison to a carbon tax if we wanted to achieve the same reduction in greenhouse gas emissions. So these are some of the considerations that one has to take into account when thinking about policy measures. Now, there are a number of complications. I mentioned some of them. I think in the interest of time, I better move on. I think I also should move on here because we are already at about 5. So let's put all these components together. So we have made a projection of energy of travel demand, passenger kilometers traveled. We have looked at energy over PKT, how it would evolve in a base case at very low oil prices, constant technology case, as compared to a case in which we could actually exploit the maximum potential of technologies, 30 to 50% reduction for new automobiles and aircraft over the next 20 years. And there's, of course, some opportunity also over the next 50 or 40 years or so to reduce the carbon content or greenhouse gas emission factor of energy, of transportation fuels. So if we do that, then we have here 2 pictures. One on the top is the world, and on the bottom we've got the United States. Historically, what we show is life cycle greenhouse gas emissions. So we have 4 different components now. We look at light-duty vehicles, we look at low-speed public transportation, at high-speed transportation, and at the fuel and vehicle cycle. That's the amount of energy, or in this case, the amount of CO2 emissions, or greenhouse gas emissions that are released during the production and supply of fuels and the vehicle, and the retirement of the vehicle at the end of life. So we have essentially seen this development already, significant growth between 1950 and 2005, and in a constant technology scenario, we said, I think, roughly 2.5 to 3 to 5, I believe, increase in greenhouse gas emissions. Now, if we implemented the maximum or the most fuel-efficient technology that would come online, let's say 30 to 50% reduction over the next 20 years, phased that into the market, and allowed for 20% second-generation biofuel, then we would achieve a significant reduction in terms of greenhouse gas emissions compared to the constant technology case. But on a global level, we would still experience an increase here. Now, you would need to have fuel prices of about $1.50 per gallon, per liter, so about $5 per gallon of gasoline in order to achieve that. You would then have also some demand reduction here because of the fuel price elasticity, but that's probably negligible as compared to the technological potential. It looks more promising in the industrialized world. Here on the bottom, we've got the case for the US. Again, significant increase between 1950 and 2005. 2 economic growth rate scenarios, roughly a doubling by 2050. And then we could actually stabilize or even slightly reduce life cycle greenhouse gas emissions by 2050 for both of these scenarios. Again, because of the lower growth in transportation demand and the assumption that we have a slightly larger potential for these technologies to implement here because of some capacity constraints in the developing countries. Now, the message of this chart, and I have to speed up a little bit, is it repeats some of the numbers we have just seen in terms of the chart. But what it does is the yellow row is the important one here. And if you imagine that we try to achieve a 550 ppm stabilization level that we discussed at the beginning of this talk, then the question is, how would transportation CO2 emissions evolve as compared to a constant technology scenario? So we've got a fuel price and we've got a carbon tax on top of it. And the carbon tax turns out to be about $30 per ton of CO2 in a very optimistic case of a global participation in terms of reducing, in terms of a carbon price and effort to reduce CO2 emissions. In that particular case, the fuel price would increase to about 80 cents per liter, about $3 per gallon. And the impact on transportation would be relatively modest, actually. We would still rely on mainstream technology. There's no radical technology change. Still mainly dominated by a mechanical drivetrain, more fuel-efficient engine, less driving resistances, but by and large the same type of technology as we operate today. And there would be some introduction of second-generation biofuels. So what does this mean? If we look at the consumer impact that we wanted to look at as a result of climate policies, well, we would have higher fuel prices, potentially higher vehicle costs, but at the same time, income continues to increase. And also the higher fuel efficiency of these vehicles would mitigate some of the price increase. So overall, consumers would not be very strongly affected by climate policies as it relates to transportation. And as a result of that, as I've pointed out in red here, should travel demand ever saturate? Most likely not because of global warming policies. So we are most likely to continue to evolve along the growth trajectory that we have seen at the beginning. And also, as we said, there's a continuous dominance of mainstream technologies, so consumers would not be confronted with a radical change and adaptation to different technologies. So that's the last slide now I'm going to show. What does this all mean? What are the choices? Well, government has to think about, or governments, plural, have to think about a number of issues. One is the type of policy measures to impose, and in order what did I write here? Type of policy measures to change consumer. Okay, I think it's self-explanatory. They can use market-based regulation or a combination of both in order to affect consumer and industry behavior. And then one question is, should it be a single policy approach versus a portfolio of measures? Well, already, as I indicated before, there's a whole range of policies already in place, whether these are CAFE standards or low-carbon fuel standards, R&D, subsidies, and so forth. So it's highly unlikely that one single policy measure would be introduced, although in theory, one regulation or one carbon tax could do the job. And there's also the question, should governments strive to economy-wide measures or look at passenger transport alone? Well, from a CO2 perspective alone, economy-wide measures would make more sense because they are cheaper. But if there are other concerns in addition to CO2 emissions, then it makes sense also to look at the passenger transport sector or transportation sector in general in isolation of other sectors, and also perhaps put a separate policy measure in. And obviously there is an opportunity for R&D investments I had no time to get into. Now, industry action strongly depends on government, of course, but a few certainties exist. Foremost, we have seen at the beginning that the greenhouse gas emission problem is not going to disappear. I think the opposite is true, simply because of economic growth and structural change in the economy, emissions are going to be more and more located or released from the transportation sector. So this is a high priority issue to remain. And then second, where should industry place the R&D investments? Improving technologies in terms of reducing fuel consumption is a strategy that makes complete sense for a number of reasons, and two are indicated here. Well, it mitigates the trade-off between climate change and oil dependence. It serves both, which could otherwise induce governments to heavily invest in much dirtier fuel alternatives than oil. And what I could not show you in terms of the interest of time is that if you look at the substitution, introduction of technologies that you can model, then and you impose a carbon tax on the entire economy, then what you can easily demonstrate is that you're shifting from one technology to the next cost-effective one as a way of minimizing the cost for CO2 emission reduction. So improving mainstream technology makes also sense from that perspective. So ultimately, we have seen that there's enormous potential for reducing greenhouse gas emissions through technologies. It has been in the past, and also here we have suggested that 30 to 50% further reduction is possible by 2050 on a fleet basis, and potentially much more than beyond. But whether these technological measures are sufficient, that's a different question. And ultimately, we may actually think about additional ways of reducing emissions, and ultimately, we have to look in the mirror and ask ourselves whether we can actually maintain the lifestyle we would love to. Thank you very much.
Okay, great. So we'll take questions. Students, if you could, yep, you get the first go at it. No? Okay. All right. Yeah, how about you?
Do you think that given the high population densities in the developing countries, a rapid public transportation system like high-speed rails or bus rapid transportation could mitigate much of the effects of like the carbon intensity per passenger kilometer in the near future?
Well, I think if you're able of making sure that people would mainly use these transportation systems, I'm sure there is a potential. But if developing countries follow the model of the industrialist world, namely to expand the cities by tearing down some parts of the old city structure and building highways instead and allowing easy access to and egress from the cities with the automobile, then I think this strategy will not work. I think it's a transportation policy, urban planning issue that definitely should be looked at, given the potentially limited opportunity that technologies can provide. Also, of course, by themselves, they're very large.
But do you not think that, like, given that urban population is much denser in developing worlds, like China, India, or in many parts, that high population density actually facilitates public transportation because there's more people actually going through public transportation becomes more cost-friendly?
I think the answer is of course, but the question is whether you can maintain the high population densities. If you look at the history of evolution of transportation systems, as it was in London, for example, then you can observe that with the introduction of any faster transportation mode, so first you had in the 1800s, you had the horse-drawn bus, then you had the first subway, then you had, first motor bus and passenger car. What you could observe is that the urban population density has declined and the population density outside the city has increased with the overall effect that the total population density has declined. So you need, I think, very sophisticated urban planning measures in order to continuously exploit the high population density and obviously maintain those. But it's an opportunity which should definitely be pursued.
Okay, all right, next.
A quick question, maybe you've addressed this and I didn't catch it, but it seemed like you were focused primarily on the passenger side of things. What is the breakdown in terms of passengers versus cargo, and how does cargo transportation play into all of this? It seems like that would introduce a whole different set of variables.
Yeah, so you didn't miss anything. I only looked at passenger transport. In terms of relative importance, at very low levels of economic development, you have a much larger share of freight transportation because you need freight to build up the basic infrastructure and carry the heavy stuff and so forth. But as soon as countries begin to motorize, you see a drastic increase in energy use in terms of passenger transportation. But still today, freight transportation is about, in the US, it's about 35 to 40%, I believe, of total energy use, and larger on a global scale. In freight, you would observe very similar patterns in terms of shifts toward faster modes, whereas you have the travel time budget here as a sort of a determinant or driver of mode change. You would have the average value of the commodity that you transport in freight. So at very low levels of economic development, you have very low value freight like cement and concrete and stones, and in order to build up the basic infrastructure. But once this is done, then you continuously ship commodities that are much higher in terms of the value, whether it's cars or computers and so forth, which are then typically not transported by ships or by, let's say, barges or railways, but by trucks and by aircraft. So you see a very similar pattern towards faster modes and, unfortunately, higher energy intensity. So there are a number of trends in the system that unfortunately move us towards ever higher levels of energy intensity, whether it's the shift towards faster modes, whether it's changes in society or other factors.
Do you think the adoption for new technology, do you think there's potential for faster adoption by industry than by passengers? You know what I'm saying? If you're looking at truck fleets, if a company can adopt with that, could you see faster penetration of fuel-saving technologies in cargo freight industry than passenger, and might that be a good place to start?
Well, I'm not so sure. The lifetimes of trucks I'm not sure they're much shorter than of cars. And typically what happens after 3 or 5 years, they're resold to other countries. Also, as a result of that, industry only typically looks at 3 years amortization rates. If you offer them more fuel-saving technology and doesn't pay off after 3 years, they're not interested. It's very similar to passenger cars.
Okay, all right. Hey, Adam, and then we'll take one more after you.
Do you think that the potential introduction of qualitatively different telecommunications technologies, something that's sort of a step change, might have a different sort of effect than previous telecommunications technologies? So I'm thinking of like these sort of HD telepresence systems. Or to put it another way, the effective speed of transport of electrons, if we're going to try and travel 250,000 kilometers a year, is something like an HD telepresence system is the effective speed of that infinite. And so, or would it just have this more of the same effect of inducing us to make friends in Europe so we want to go visit them? What do you think?
I think the jury is out. We have to see, but well, there's maybe a potential, but ultimately you may want to meet up with your partner on the other side of the link and have a beer or something else. I don't know. History has suggested that we shouldn't be too optimistic, I think, about these potential opportunities.
Okay, all right. I think we had one here, and sorry, it's going to be the last one, but hopefully, Andreas, you'll be at the reception. Yeah.
My pleasure.
Okay. All right. Yeah. Go ahead.
Can you talk a little bit about the high-speed energy, the high-speed trains recently launched in Japan, and how that could be a role model for the ones we have planned by the Obama administration in the United States, and how that perhaps could obviously help reduce the emissions?
Well, I can try to give you a short answer to that. High-speed rail offers certainly opportunities, but only in certain corridors where you get the sufficiently high occupancy rates. And I think there are only 10 or 11 of these corridors designed for the US. Now, if you look at Japan and the way how the various cities are located, then you realize that actually they're all along one main railway line, more or less. So that's a fantastic opportunity to connect those through high-speed rail. It's very different here in the US, and it's also different in Europe. And there are corridors that where it makes economic sense, and there are many corridors, potential corridors, where it makes less so. It's important to consider that the energy intensity of air travel, for example, very strongly depends on the stage length. There is an optimum stage length with a sufficiently long cruise stage in which you have relatively low energy intensities and in which you can compete with high-speed rail. And then, of course, it depends on the fuel you use for generating electricity. So all these factors need to be looked at very carefully. But even in the Japanese case, if you look at the link between Tokyo and Osaka, there is high-speed rail. But also they're operating Boeing 777s and 747s between these two cities because high-speed rail alone cannot accommodate the capacity. So it is definitely, for suitable corridors, it's an opportunity, but I'm not sure you can extrapolate it too much.
Okay. All right. Well, thank you very much. That was fabulous.
My pleasure.
For more, please visit us at stanford.edu.